Assalamualaikum and very good day to you. Welcome to CDB 2043 Reaction Engineering. I am Dr. Raihan. So let's have some brief introduction on reaction engineering with chapter 1 on mole balances. So this is part 1 of chapter 1. I hope you will be able to understand this lecture. There will be a short quiz for you to answer after finishing this video. Happy watching and all the best. Before I move in details, let's just have an overview of this course. So this course are divided into two main parts. The first part is the basic knowledge. So in this part you will learn on 4 chapters as a building blocks for your basic or fundamental understanding on chemical reaction. And later in the application part, you will apply your knowledge of reaction engineering in designing or solving chemical reaction engineering related problems. So the focus on the application will be on chapter 5, chapter 6, chapter 8 and chapter 13. So this is the learning outcomes for this lecture. So by end of this lecture, you should be able to firstly explain the importance of reaction engineering knowledge, and then secondly, you should be able to define the reaction rate, and last one, you should be able to explain or describe different types of chemical reactors. Okay, so first, let's have a look at the definition of chemical reaction engineering. So from Levenspiel, he stated that chemical reaction engineering is an engineering activity that concern with the exploitation of chemical reactions. And the main goal is to ensure that the design and operation of chemical reactors are successful. And it also sets chemical engineering apart as a distinct branch of engineering profession. So for you to be a graduate chemical engineer, you must have the knowledge in chemical reaction engineering. Okay, so apart from being a chemical engineers, why is it actually that we need to know about chemical reactions? So chemical reaction is a heart of a process, of a chemical process. So as a living organism, you need heart to stay alive. So similarly for chemical process, reaction is the vital part of the whole process. So for you as a human, when you eat food, because of the chemical reaction occurs in your stomach, it turns into fuel for your body, so you have the energy to do activities all day long. And also it can make fireworks explode. So during celebration or Happy New Year or Merdeka celebration, you can see the fireworks. It is because of the chemical reaction occurs. So without chemical reactions, nothing would ever change. Atoms would stay atoms, new molecules wouldn't be formed, no organism also could live, even us as human. So if matter didn't react with other matters, the universe will be extremely boring. So in a chemical process, a reactant or one chemical will undergo several processes to produce a product, which is another chemical. So for example, production of polypropylene, which is used to make chairs, containers, plastic bottles, lab apparatus, etc. that you use in your daily life. So the raw material is from LPG, and after the cracking and separating process, you will have propylene as one of the product. So the propylene is what is being used to produce chairs, to produce the plastic products. So the propylene will go through polymerization process, which is one of the chemical reaction process in the chemical treatment step. So this is the step where the chemical reaction occurs. So from raw material is going through the chemical treatment step and then going through a physical treatment to purify the products, then only it can produce another product. So these are some examples on reaction processes. So remember the example of polypropylene just now. So this is the process of producing propylene. Okay, so which is the raw material for producing plastic products. So propylene is actually a product from chemical reaction, and there is also few other examples of chemical products from only one raw material, which is LPG. So when we talk about chemical reaction, the main question is, how do you know whether the process is economically feasible or not? Okay, so the goal is to produce an optimum process. Produce optimum process so that it can lead to maximum desired product. Maximum product which lead to the maximum profit. So end of the day, it is always how much profit you can get from the process. This is always on maximizing the profit. So when we talk about chemical reaction, the most important term that you should understand is rate of reaction. So rate of reaction indicates how fast a number of moles of one chemical species being transformed to another chemical species. So it is how fast is the species A lost its identity to a species B. Okay, so in a simple way, say you have a few materials used to bake a cake. So we call it as species A. And after few hours, you mix the materials, you mix the flour, the eggs, and after few hours, put in the oven and you get a cake that is species B. So the time required for you to convert from A to a cake a species B is the conversion rate, the reaction rate. So what is the chemical species here, and how do we define the chemical species? Chemical species is any chemical component with a given identity. So the chemical species can be determined by its kind, the number, and also the configuration of the species atom. Okay, for example, here we have cis-2-butene and trans-2-butene. Both have the same number of atoms, which is C4H8. But because of the difference in term of configuration, you can see there's the difference in term of configuration of the atoms. So we consider this as two different chemicals, and also it have different chemical and physical properties. Okay, so now we know about the chemical species. What is chemical species? But now in an experiment, you mix together chemical A and B, but both liquids. So how do you know that chemical reaction has occurred? So reaction occur in three ways. It's either change in number of atoms, change in the structure, or change in the atom configuration. So chemical reaction occurs, so the first way it can occur through decomposition, where it's broken, one chemical species is broken down into two smaller molecules or atoms or fragments. So here you have cis-2H6 is converted into H2 and C2H4. And also, second way is through combination, where it combines two or more smaller molecules and atoms to form a larger molecule. It is the reverse of decomposition. Decomposition, you break from larger molecule to smaller molecule, but combination from smaller molecules combine to get one larger molecules. And another way is through isomerization, which is the change of configuration. For example, the previous we have cis-2-butane can be converted into trans-2-butane through the change of the location of the atom. There are two ways to define reaction rate. So let's consider we have a reaction of A producing B. So the reaction rate can be defined as how fast species A is disappearing, we call it rate of reactant disappearance. We have the minus sign, or how fast species B is producing, I mean the rate of product formation. So say you have a concentration profile with time, concentration versus time. So you have A decreasing but B is producing. Okay, so there are two ways to write the units. This is number of moles over moles reacted over the volume times the time, or number of moles reacted over the catalyst weight times the time. So for a reactant, it's number of moles reacted, but for the product, it's number of moles formed in the system. So for the second unit, number of moles reacted over the catalyst weight times the time, this is for the heterogeneous system. So heterogeneous system where the system involved with more than one phase, for example, liquid reactant with solid catalyst or gas with a solid. So for the heterogeneous system, we write the reaction rate as minus RA, but with the prime symbol to denote the heterogeneous system, which normally involves solid catalyst. Okay, so reaction rate is an algebraic equation, and it is intensive properties, meaning that the reaction rate depends on the concentration of the reactant, the temperature, pressure, or type of catalyst in the system. So, but be careful with the definition of reaction rate, because the DCA, the change of concentration over the change of time, is not the definition, it's not the general definition of reaction rate. Okay, why I said that? Because say you have DCA, change of concentration over change of time equals to minus RA, is only valid for batch system, where it is a closed and rigid system. So it's not general definition for the reaction rate. And last one, reaction rate is not influenced by the type of reactor. It is either batch or CSTR, the reaction rate is the same. Okay, so for example, we have a reaction of sodium hydroxide and acid in a CSTR. So CSTR operated at a steady state with the inlet and outlet flow rates the same. So it is perfectly well mixed system, meaning that when you add sodium hydroxide, it will be converted straight away to the product, means that the reaction occurs very fast. So the since this is perfectly well mixed, so the samples, concentration of the samples taken at the morning, maybe 10 a.m., will be the same as the concentration taken at 5 p.m. For example, you check the concentration of sodium hydroxide at 10 is 2 molar. So say you have 2 molar at 10 a.m. But at 5 p.m. when you check again the concentration, it will still remain 2 molar. So meaning that the DCA concentration of the change of concentration of NaOH is 0 over the time. But does it mean that there is no reaction occurs in the system? It's not right. So that's why we cannot say that this. So that's why we cannot say DCA over DT equals to minus RA as a general definition of reaction rate. This is only valid for batch but not valid for flow reactor. Okay, by now I hope you have a clear understanding on what is a reaction rate. Okay, now we look at the 4 basic reactor types. We have batch, CSTR, PFR, and PBR. So the selection of reactor depends on the reactant phase. So normally for industrial application, for liquid phase process, we use semi-batch or CSTR, while for the gas phase process, we use tubular reactor. Okay, so for batch reactor, the physical shape is like a tank, but we have a stirring system inside the reactor, and it's not for a continuous process. So this is ideal for high conversion process with long residence time. Meanwhile, for CSCR, it also looks similar to the batch reactor, but it has the flow in and flow out continuously. So it used for continuous operation, and it's perfect mixing, and also run at the steady state operation. Okay, another 2 type of basic reactors are PFR and PBR. Both are used for continuous operation. For PFR, it is in cylindrical shape and is normally used for gas phase reaction. Meanwhile, for the packed bed reactor, PBR, also for continuous operation, but it involves the use of catalyst. So the mass of catalyst inside the reactor is more important than the volume of the reactor. It is also in a cylindrical shape, and the other criteria is similar to PFR. Okay, now we have finished our lecture for part 1 of this chapter. So before I end this lecture, let's just recap what we have learned today. So by now you should be able to explain the importance of reaction engineering, and also you should be able to define what is reaction rate, and lastly you should be able to describe 4 types of basic reactors and also their application. So in the next lecture of part 2 for chapter 1, you will learn to develop the general mole balance equation in order to design the reactor. Okay, now is the time for you to answer a simple quiz to assess your understanding on this lecture. Good luck.